This is part 3 of Lecture 2, PIC microcontrollers, and in this part we'll look at interrupts. Let's say your program is running its main code, and then suddenly an interrupt occurs. So when an interrupt happens, your program counter updates where it's pointing to and updates it to and points to a separate area, what we call the interrupt service routine. Now these interrupts are the same interrupts that we looked at in the previous video, where we were setting up the interrupt flags for timers 0 to timer 2, and they're not the only registers that have interrupt flags, and the peripheral modules available for PIC18 have these interrupt capabilities basically. And at this point you run your code, an interrupt occurs, and you may go into this interrupt service routine. Now it is your responsibility as a programmer to handle what happens when an interrupt occurs. So specifically, let's look at the example of one of your timers overflowing, thus interrupting your main code. So you want to code specific things to then reset the flags. You want to apply what these interrupts mean. So for example, to interrupt it, to wait for a millisecond, it needs to be interrupted after 156 clock cycles. So when an interrupt occurs, you know a millisecond has occurred. So what should you do in your main program or in your interrupt service routines to then update these occurrences? And then to finish it off, you actually need to find a way to then return from the interrupt service routine, so the program counter actually goes back into your main program. So in a way, it's almost as if it's a function that you're calling, but rather than your software or your program code that does it, it's the hardware that controls these things. So your code will set up your different modules to interrupt at specific intervals or specific events. And then when the interrupts do occur, the program counter then points to these interrupt service routines, which handles what it needs to handle, and then goes back into its main program. So rather than a software subroutine or software function, it becomes a hardware activated function. Interrupts from your microcontrollers are controlled and configured in the int_con register. Now there are also a few registers associated with int_con that deals with peripheral interrupts, such as the PIE registers, so there's 3 of them, and also the PIR registers. Now I'll let you take your time to look through the datasheet and look through these specific registers, as they handle all the interrupts that occur with your PIC microcontroller. So as mentioned before, the program counter points to these interrupt service routines when an interrupt occurs, and therefore the most important part is that the interrupt flag bit must be cleared in software to avoid these false interrupts or recursive interrupts. So if that interrupt flag bit is still 1 when you exit from the interrupt service routine, that would automatically flag an interrupt before it even points back into your main program. And that's why in the previous slide I mentioned that you as a programmer has some responsibility when it comes to the interrupt service routine. Now in assembly, they have a specific instruction called return from interrupt, or RETFIE, that exits this interrupt routine and goes back into your main code. And in C, this is a bit different. So let's say we have a main function which sets up the interrupts and runs your normal code, and you have a special function that you need to declare called void of type void and interrupt. So this is basically saying that this is in a different set of address location, and that's just your interrupt service routine. So do take note of this. It's not necessarily required for this subject, but this is the way to program in C the interrupt service routine. So as mentioned before, the interrupts can come from many sources, both internal and external. So all the modules should have some interface with the interrupt or the interrupt configuration or int_con registers, and something to note as well that there are two priority interrupts. So given two interrupts that occur at the same time, if one has a higher priority, that will activate first, or that interrupt service routine will run first rather than the lower priority interrupt. When an interrupt occurs, there are a few things that happen in the PIC microcontroller itself that you should know as a programmer. So specifically, when an interrupt occurs, your current instruction finishes executing. Now this is the most important point in point 2. The global interrupt enable bit in intcon is cleared to prevent additional interrupts from occurring whilst the interrupt service routine is finishing or executing. Now this means that before you return from the interrupted service routine, you need to reset that bit, or else none of your other interrupts will occur. Now, in assembly, which is a low-level programming language, there are also a few other sort of housekeeping rules that you should be wary of. So these include the context of where your program is currently. So that's all your variables and all your registers which reflect the current state of your program execution. Now remember that there are C libraries which handle these specific housekeeping rules. So the libraries do handle that, but it is worth noting what they are. So if it is the case that you're writing in C and your interrupt service routines are throwing weird errors, or it's producing a result that is unexpected, it might be worthwhile remembering a few of these underlying things that are happening and trying to debug that from there. So let's look specifically at our example of our timer modules. So when a timer times out, depending on which timer you're using, there are specific peripheral registers which interrupt. So there are a few specific ones, as mentioned before, that you should look at. And specifically for timer 0 to timer 2, you should look at PIR1, or so PIR is known as Peripheral Interface Request. You have PIE, which is Peripheral Interrupt Enable, and your intcon register, which is your interrupt control register. Now, I won't go through too much in this slide, as it vaguely sets out what happens when timer 2 overflows, or what happens when timer 1 overflows. And that's for you to find out through the datasheet. So specifically in your datasheet, for each one of these timer modules, there will be a section detailing what happens when the specific timer overflows. So in this example, when timer 2 overflows, it sets the PIR1 bit 1. So you need to test this bit to see if it's overflowed. And then on startup, that defaults to 0. The enable bit defaults to 0, so you need to set that so the interrupt is enabled. And similarly, as mentioned before, the global interrupt enable bit has to be on, or else the interrupts will not be processed. And remembering from previous slides, when an interrupt occurs and you go into the interrupt service routine, your GIE bit turns off to prevent any additional interrupts occurring. So let's look at an example that you can use interrupts, or the interrupt service routine, for. So let's say we were trying to implement a 500 millisecond delay. So rather than a 1 millisecond delay, which for a 20 megahertz crystal is 5,000 clock cycles, you want to do a 500 millisecond delay, which means you need to wait 2.5 million cycles. Now, if we're using timers, we don't have to count how many cycles or how many ticks has occurred, but rather the timer will act as the counter or the timer to tell you when 500 milliseconds has occurred. So think about how you would initialize the timer. So it doesn't have to be timer 2, it can be timer 1 or timer 0. And think about how you would set up the interrupted service routine function. So a few slides back, we looked at the syntax, the C syntax on writing this ISR, or interrupt service routine. And think about how your program code would occur, and think back to the first part of this lecture to represent your task or your problem in a diagram. So let's say we have a function called 500 delay, and I want you to look at how you would implement this. Now, this is not part of your assessments for assignment 2. However, it's worthwhile knowing for your future works with the PIC microcontroller. So there are a few things that you might want to look at. So let's consider whether it's possible to do the 500 millisecond delay with other timers. You also want to consider how about using a counter to count smaller delays. So potentially you could look at the prescalers and find out that it won't reach 2.5 million clock cycles or one overflow. Then potentially you want to look at having a counter, for example, a register called count, that counts however many times it has overflowed. So let's say rather than setting the timers to count 2.5 million clock cycles, you might just tell it to count 500,000. That way you check whether count is 5, and if it is, then you know 2.5 million clock cycles or 500 milliseconds has happened.